Alright, so we're talking about scalar projections, scalar products and projections, often called the dot product or the inner product for our vectors here. So if we just take a look at first the definition of what is called A dot B. So if I take two vectors and I take the dot product, that is equivalent to the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle in between the vectors. And that's really what we're going to be interested in, is that angle between those vectors. So if I take two general vectors, A and B, and there's my angle. What we're really looking for is what the dot product is telling me is if I look at x over a, which is cosine of theta, x is a cosine theta. So that whole piece in front of our value is we were to take x and multiply it by the magnitude of b. And we're going to use that idea to look at what's called a projection later on. What we want to look at, though, is the dot product is a scalar, which means that it's a number. It's not a vector. It just has magnitude. It has no direction, which is going to allow us to find, again, these projections down the road. So if I was to take two vectors that make an acute angle, well, the magnitude is always going to be positive. The length of the vectors is positive. But the angle in between them, if it's acute, cosine is positive for an acute angle, so my dot product is positive. It's greater than 0. If I look at an obtuse angle, again, I have where the magnitudes are positive, but the cosine of an obtuse angle is negative, and so my dot product is less than 0. If I look at a right angle, well, the magnitudes are positive, but cosine of 90 degrees is 0, and so my dot product is 0. So that's two dimensions. That's kind of how those work out. What we're really interested, though, in this chapter is three dimensions. So if I look at a three-dimensional vector, so if I take a general vector and another general vector, so A and B, where it's as general as it can be, and if I look at the dot product of those two, what we're going to do is we're going to think of distributing our dot product here. So if I was to distribute all this through, we're going to assume that that's a valid operation on the dot product. I'm going to get this big mess. So I'm not going to write the whole thing out because there's a lot to it. But basically I get A times D, and then I dot I, and then A times E, I dot J, plus that repeats all the way down to the end where I get C times F, and then K dot K. And we have to remember what the I, J's, and K's stand for. There are unit vectors. So if I look at I and J, they make a 90-degree angle. That's how they're defined. And we just looked at before, well, the dot product of a 90-degree angle is 0. So that whole term is going to go away. So those are going to cancel out. Anything where I have non-like unit vectors, I'm going to get a dot product of 0 because the angle is 90 degrees and cosine of 90 degrees is 0. Also, if I look at the same unit vector, so K and K make an angle of 0 degrees, and cosine of 0 degrees is 1. So this whole thing becomes the magnitude of K times the magnitude of T times cosine of 0 degrees. Well, the magnitude of K, since it's a unit vector, is 1. So this looks like 1 times 1 times 1, or 1. So if I multiply CF times 1, I just get CF. So if we do that for all of the possible combinations of that distributed dot product, what we're left with is something pretty simple, where I get A dot B is AD plus BE plus CF. So all that said and done, we just multiply the like component values. So A times B, A times D, B times E, and C times F, and add them together. All right, quick example. Let's say we have our vectors A dot B, where A is 2i plus 3j minus k, and B is 4i minus 2j plus 3k. And I want to find the dot product. Well, doing what we just did before, I just multiply the components, the values in front of the components, and I'm going to get -1 as my dot product. So that's my dot product. We also have the other expression where it's the magnitudes multiplied times cosine of theta, and we're going to use that for something called the projection. So why does it matter? Well, we're often interested in how much of one vector is projected or is in line with the other vector. So if we look at the blue vector and the green vector, there's some piece of the blue vector that is in line with the green vector. Not the whole thing, but a portion of it, and we call that the projection. The projection is our orange vector there. So it's that piece, that component along B that makes up vector A if I was to go head to tail. And to really figure that out, since I'm going to know the length of A, I need to know what that angle is going to be. So we're going to use the dot product to figure out the angle. because all it is, our projection, is the magnitude of A cosine of theta times vector B. It gives me that vector P, which is just simple right triangle trigonometry, but looks complicated because it's in this realm of vectors. All right, that is just a scalar value. So we're just really scaling vector B to be just in line with that orange value. All right, so we can take a quick look at a problem and talk about how it works and how we can attack it different ways. Let's say that we are given, this is in the book, this is number 19, where we have two forces acting on a sailboat cleat. So some point of attachment on a boat deck, and we have two ropes that are pulling on it, given by those force vectors. And we're asked to do a couple of things. We're asked to find the resultant force vector and the force in the y direction. So we're looking for that component in the y direction. There's an easy way and a hard way, but let's look at what we have going on here. So resultant vector means I add my two force vectors. So there's my first force vector, there's my second force vector, and I add them together, and that's my resultant force vector. Now, if I want to know the y-axis component, well, that's going to be 120 because that's what's in front of J. But we could figure it out by looking at projections, and that's what we're going to do down the road. So let's say we didn't know that, but we did know that we could figure out a projection along the y-axis. So we have our resultant, I have the J value, which is along the y-axis, and I want to know what that piece is. What projection do I get along our J component? Well, I apply my dot product. So I have the magnitude of R times the magnitude of J times cosine of theta. That becomes the magnitude of R times 1, because 1 is the length of my unit vector, and cosine of theta. I don't know what theta is at this point, but I know that it's the angle in there. But I also know that the dot product is the multiplication of all of our values of like components when we did before. So that's also equal to 120. If I multiply through 45 times 0 is 0, 1 times 120 is 120, and 15 times 0 is 0. So if I was to solve for theta, I can take a cosine inverse and I get 21.6 degrees. Now, assuming I don't have an approximation error, I plug that back in to figure out my projection, the force along the y-axis. So I plug it back in. It's the magnitude of R times cosine of theta, which, as we just figured out, and works out to be 120. So that's how we're kind of going to go between these things. If we have two vectors, we can find the angle. If I can find the angle, I can find a projection along those values.